In this lesson, we look at radioactive decay, and I give you some definitions, and we look at some patterns. Here are the objectives. Now, in radioactive decay, we have a parent nucleus that spontaneously turns into a daughter nucleus. It becomes a whole new element, and it does so by emitting an alpha particle, a beta particle, or a gamma ray, and we've looked at those kinds of radioactive emissions already. Now, that process is random. When we have a whole bunch of parent nuclei, we can't tell which one is going to turn into a daughter nucleus, and it is spontaneous. It's not influenced by outside effects like heating the sample or by exposing it to chemicals. However, it does follow a rule. Let's look at an analogy to understand that kind of rule. Here's the analogy. I'm on the random.org website. I've got 45 dice. I want you to imagine that each die is a parent nucleus. And when I roll them, whenever I roll a 1, that parent nucleus is going to decay into a daughter nucleus, and I'm going to have to remove it, and then I would roll again. So here I'm going to click roll again, and I'm going to look for all of the 1s, and I'm going to cross them out. So I've got a 1 here, and here, there, and there. So what I want you to notice is that there's a random element to this. I can't tell which of the dice is going to come up a 1, but there is something predictable in that I know that there's a 1/6 chance for any individual die of coming up a 1. Now I take a look at these and I count up the ones. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different ones, so I can remove them and repeat the process. So now I've removed them. I started with 34 dice and I've rolled them again, and once again I could remove the different 1s. So I've got 1s in each of these places. Now notice that the more die I start off with, the more 1s I'm removing, just because that 1/6 chance over more die means more are going to get removed by probability. And again, notice that the process is random and I can't predict which of the dice is going to come up a 1. Now this is the half-life gizmo from explorelearning.com, and we've got a bunch of radioactive nuclei shown here in red, and in a moment we're going to start the simulation and we'll see them decay into the daughter nuclei shown in gray. I want you to imagine that each radioactive parent nucleus here is like an individual die, and we're rolling them again and again. Each time a 1 comes up in the dice simulation, we remove it. Here, as the radioactive nuclei decay into the daughter nuclei, they'll show up as gray. You can think of that as dice that are no longer able to be rolled. If I start this up here, you can see that we get a lot of decays right at the start, and then the process seems to slow and we have fewer of these decays per second, still going on now. Now imagine that these are individual dice, and each one has a 1/6 probability every roll of turning up a 1, we'd have lots of 1s come up right at the beginning, and then fewer 1s as we're rolling fewer and fewer. Showing that again, I've got lots of dice, so I'm rolling lots of 1s. The 1/6 probability of coming up a 1 on any one roll doesn't change, but as I have fewer dice to roll, I just get fewer 1s coming up. Here, we see that as fewer decays per second. We see the process slowing. So that's the analogy between rolling dice and radioactive decay. So let's think about this a little further, and we're going to think about two things. We're going to think about the number of nuclei, or the number of dice, and we're going to think about what we'll call the activity, which is the decay rate, the number of decays per unit time, or if you want to think of it this way, the number of dice coming up as 1 per roll. And I'll define the activity a bit more mathematically in a moment. Now, if we have this constant probability, then if I graph the number of, and this is parent nuclei we're looking at, the radioactive parent nuclei. Let's say we start with 100. I'll write 100. Let's actually mean 100 million. That's more realistic, but we'll just write 100 here. If I start with 100, then there's a characteristic pattern we see from this constant probability of coming up a 1 or of decaying, and that's an exponential curve. And if I draw that properly, then if I'm graphing the number of parent nuclei versus time, then the time it takes to get from 100 nuclei to 50 nuclei, so that's this time here, and the time it takes to get from 50 nuclei down to 25 nuclei, that's this time here, is the same. And I've chosen those times or those numbers of nuclei specifically because I'm having the number of nuclei. So we call this the half-life. I'm going to write that as T sub 1/2. And that half-life is a characteristic of the particular parent nucleus, the particular isotope we're working with. If you saw on the previous simulation, the half-life for that isotope was 35 seconds. So this would be 35 seconds, this would be 35 seconds, etc. Every 35 seconds, we can expect to have the number of nuclei. Now we can also think of the rate of clicks that we were hearing as the decays were happening, the rate of decay, and that would be the slope of this graph. So I'm going to draw some tangents here, and you can see that the slopes are getting less extreme. They're getting less steep, and we saw that as less decays per second. Now that slope has a rise of delta n, that's the rise here, and has a run of delta t. So the slope of this graph is delta n over delta t. Now it's a negative slope. In other words, this rise over run is negative. So if we put a negative sign in front of it, now this whole thing is positive, and we're going to define the activity that way. The activity is the negative of the slope of this graph. It's negative delta n over delta t. Again, the activity is the decays per time. So activity is decays per second, and we give the unit of becquerel to 1 decay per second. So 1 becquerel means that 1 parent nucleus is decaying every second. Now it's a unique feature of exponential curves that when you take their slopes and graph them, you get another exponential curve. So if I were to graph the activity now against time, I get another exponential curve like this. Again, what I'm graphing here is not the number of parent nuclei anymore, but I'm graphing the number of clicks per second that we're hearing out of the Geiger counter or that we saw in the simulation. Now, this could be any kind of number. Let's say this is 500 becquerels, and then down here is 250 becquerels, and then 125. And what's really interesting is that the half-life on this graph, so to go from 500 to 250, I haven't drawn this super well, but that time there, in other words, that time there, and to go from 250 to 125, again, this is the half-life, and this half-life and this half-life are the same. So this 35 seconds appears on both graphs, whether we're talking about getting from 100 million nuclei to 50 million nuclei, or from a decay rate of 500 becquerels to 250 becquerels. Both of those things are going to happen for the isotope in the simulation in 35 seconds. That half-life is a characteristic of the isotope, shows up in both graphs, and they're both exponential. If you want to think about it mathematically, the graphs are vertical stretches of each other. So to define the half-life is the time that it takes for either the activity, that's the graph on the right, or the number of parent nuclei to decrease by half. And it doesn't matter which of the graphs you're looking at, it's the same half-life, here 35 seconds. Now we're going to define something else, the decay constant, which we give the Greek symbol lambda to, and that's the probability that any one nucleus will decay per unit time, and that's going to show up in equations. If you think back to the dice example, the decay constant was 1/6. That was the chance of getting a 1 every roll. The activity, A, we've already said is equal to negative of the slope on the left, but now we can also introduce the decay constant. The activity is also equal to the decay constant multiplied by n, the number of nuclei. Again, n versus t was the graph at the top left, and A versus t, the activity versus time, was the graph on the top right. And so that decay constant is actually our vertical stretch factor that relates the two graphs. To get back to the dice example, which might make it more intuitive, n is the number of dice, and our lambda is 1/6 in that example, and a is the number that we are crossing out each roll. So the number crossed out is going to get bigger if we start with a bigger number of dice. The activity is higher at the beginning when we have more parent nuclei. We see that as a steeper slope here and a higher y value here, greater activity at the start. And the activity gets less as time goes on, seen as a shallower slope here or lower y values here, because there are just less dice that could possibly come up as a 1. Before we leave this first lesson looking at the exponential nature of radioactive decay, I want to mention background radiation. If we graph activity versus time, we actually are going to tend to see an exponential curve that finds a horizontal asymptote that is above 0. We're still going to hear clicks on the Geiger counter even after all of the parent nuclei have completely decayed. The red has turned to gray in our example. And that's called the background count. I'm going to write that as A sub B. And that comes from radioactive elements in rocks, in radon gas, from outer space and cosmic rays, and so we're not going to get down to 0. Now, if we want to find the half-life of the sample that we're looking at, we have to be careful of that, and we have to subtract off the background count. In other words, we have to take the activity that we're measuring, I'm going to write that as A sub m, so that's this is A sub m, and we need to subtract off the background count in order to get the true activity of the material that we're interested in. Effectively, what we're doing is we are vertically shifting the graph downwards. So that's just something to be mindful of when we're looking at radioactive samples. We need to subtract off the background radiation. We'll look further at how to find half-lives in the next lesson.